Okay, good morning, everyone. So we will postpone the discussion of the midterm and future homeworks and the plan for the class to the end of class today. So we'll go over averages and stuff like that. And actually what we're going to be doing going forward is discussing scattering as our last major topic of the semester. But there's one more thing I wanted to talk about with electromagnetic radiation interactions with atoms. And part of the reason is I want to do today an example that will be very similar to a problem on your next homework. So the problem we're going to do is to calculate the lifetime of the 2p state of the hydrogen atom. And we're going to ignore the fine and hyperfine effects, which turn out to be small for this problem. And one thing I should mention is this example is not in the notes. And one of the reasons it's not in the notes is originally I was going to give it as a homework problem, but I thought maybe I should do an example first and then give you a different one as a homework problem. A different but similar one. Okay, so maybe we should start by reviewing what are the relevant states of the hydrogen atom. So the relevant states of the hydrogen atom, you should recall, are labeled by 3 integers, n, l, and m. N is the principal quantum number. You should think of it as having to do with the radial excitations of the electron in the hydrogen atom. And it can be 1 or any higher integer. It's important that it can't be 0. We'll see in a second why it can't be 0. There's also L, which is the angular momentum. And that can be 0, 1, 2, 3, etc. And then there's the magnetic quantum number, which is the z component of the angular momentum, which varies from minus L to L. And the energy of a state labeled NLM, remember, turns out not to depend at all on L and M. So it only depends on N. There's a degeneracy there. And it's minus that quantity, which is also known as a Rydberg. And it's famously equal to 13.6 electron volts. And this is multiplied by 1 over n squared. So if you have trouble remembering if n starts at 0 or n starts at 1, that formula will tell you. If you can remember that the energy levels go like negative 1 over n squared, then you know n can't possibly be 0. Right? So those are the negative is telling you these are bound states. And so those are the energy levels. And so if we make a little chart of them, here's the n equals 1 level, which necessarily has L equals 0 and m equals 0. That's the ground state. Then there's the n equals 2 level, where it can be L equals 0, and then there can be L equals 1. Degenerate with it. This state is the 1s state. This is the 2s state. The s refers to angular momentum 0. This is the 2p state. That's the state we're going to be calculating the lifetime of. And then relevant for your future homework, there's the n equals 3 state, which has L equals 0, L equals 1, and L equals 2. So this would be 3s, 3p, 3d. Okay, but for today, what we're really interested in is calculating the lifetime of that state. So why does it have a finite lifetime? It's because it can emit a photon and transition to the lower state. So before we do that, let's say that we're going to work in the electric dipole approximation. Okay, so before just starting to calculate matrix elements like crazy, it's a good idea to first of all figure out which ones are going to be non-zero, because we don't have to waste time computing ones that we already know are going to be zero. So remember the electric dipole approximation selection rules are that the angular momentum has to change by plus or minus 1 unit in the transition. And delta m, I'm putting a subscript L there to distinguish it from spin, which will actually play no role in this discussion at all. That can be 0 or plus or minus 1. And so somewhere in the notes is listed the electric dipole approximation selection rules and all the other selection rules. Okay, so that selection rule tells us, among other things, that 2s going to 1s is forbidden by this rule, because that would have delta L equals 0. It's going from L equals 0 to L equals 0. So that's forbidden. It's actually forbidden more generally because you can't have an angular momentum 0 state going to another angular momentum 0 state. That was a general selection rule, but this is good enough to tell us that we don't need to compute it. So that's saying this decay is not allowed. And so really the only thing, if you're calculating the second level of hydrogen decaying by emitting a photon, this is the only thing to compute. It's the only thing that's non-zero. Okay, so that's why we're worried about those states. So 2p to 1s is allowed. It's an electric dipole or E1 transition. Okay, and there are really 3 such states. Again, we're ignoring spin and fine and hyperfine structure today. So the 2p states are really 2, 1, and then m. M can be 3 values, 0 or plus or minus 1. And there's only one 1s state, again ignoring spin, is just this one. So I shouldn't say states, there's one state. And then the relevant formula for the transition in the electric dipole approximation when we emit 1 photon was fortunately relatively simple. It was 4 times the fine structure constant over 3, omega cubed over speed of light squared. And then there's the matrix element that we have to compute, which is the final state, initial state, with the position operator vector inside of it, and then we have to square it. Okay, and so as a reminder, this is a vector operator. And so the meaning of this expression is that we're supposed to compute this matrix element and dot it into its complex conjugate. Okay, and so we need to evaluate. The bad news is we need to evaluate the x hat, y hat, and z hat components. So really we have to evaluate 3 things in this operator. So I said at the beginning, we're supposed to be calculating the lifetime. This is the rate. And so last time we showed that the lifetime is just the reciprocal of that. So it's 1 over the transition rate. All right, so The next thing we should do is we should figure out what that omega is. So that omega in decay problems or in spontaneous emission problems, I should maybe put here spontaneous emission. In spontaneous emission problems, you don't have to integrate over omega. It's selected for you by the initial and final states. So h bar times omega is equal to just the final state minus the initial state. And because we wrote down earlier what the energy levels were, we know that the final state energy is minus a Rydberg times 1/2 squared, which is 1/4. And then we're subtracting from that minus a Rydberg times 1, because that's the ground state energy. And so the answer is this is 3/4 of a Rydberg, which is 10.2 electron volts. Okay, and so that tells us what omega is. We just divide by h bar. So you have to look up h bar in units of electron volts times seconds, which is 6.582 something 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 times 10 to the minus 16 electron volts times seconds. Okay, and so this works out to be numerically about 1.55 times 10 to the 16 inverse seconds. Okay, so now we know what numbers to plug in here in the coefficient, because we know the speed of light. And so everything is now going to boil down to computing this matrix element, this vector matrix element. That's going to be the hard part. Okay, any questions so far? All right, so let's write down that vector matrix element. So we have 2, 1, m, vector position operator, 1, 0, 0. We're going to do this in position space. So we're going to write this, and in spherical coordinates. So we're going to write integral 0 to 2 pi d phi minus 1 to 1 d cosine theta, 0 to infinity dr r squared. And then we want to write down the complex conjugate of the final state, which is 2, 1, m. Okay, which we can look up in the notes. And then there's psi 1, 0, 0. The ground state of hydrogen, which we can look up in the notes. And then for this, we're writing the vector position operator, r. So when we write that, what we really want to do is we want to say that's equal to r times r hat, where r times r hat is r times x hat cosine theta, or sorry, cosine phi sine theta plus y hat sine phi sine theta plus z hat cosine theta. Okay, so that part's going to go with the angular integrals because it has all the sines and cosines of theta and phi. And the r part here is going to go with the radial part. And so our strategy is divide and conquer. We're going to split this integral into the angular part and the radial part. Okay, so let's go ahead and do that. Let me write first here the angular part, 0 to 2 pi d phi minus 1 to 1 d cos theta. Okay, and then our r hat goes there with the understanding that when we write that, we really mean all of this stuff in rectangular coordinates, because we're going to have to dot this thing into itself when we're done. Okay, and then what else goes there? What else goes there is the YLM part of these wave functions. So this wave function has a y0, 0. So that's a 1 over root 4 pi. And here we haven't yet committed to what the m value is. So there I'm just going to write y1m theta phi, which might be complex. So I have to remember a complex conjugate goes there. Okay, and then what's left over in the integral is integral 0 to infinity dr r squared. This r right here comes next. So there's another r. And then we have to look up what the radial wave function parts of these psi's are. And so for the 2, 1m state, it looks like this: 1 over 2 Bohr radius to the 3/2, r over Bohr radius square root of 6, e to the minus r over 2 Bohr radius. And then there is finally the same thing for the ground state of hydrogen, which is 2 over Bohr radius to the 3/2, e to the minus r over Bohr radius. Okay, so I think that's it. This we're going to call I radial for integral radial. And this part we're going to call I angular. So it depends on m. We're going to do this for 3 different values of m. But not only are we going to do it for 3 different values of m, but it's also a vector because it depends on r hat, and r hat is this stuff. Okay, so this is actually a vector as an integral. All right, so now let's dispose first of the radial part because it's relatively easy. I radial is 1 over square root of 6. And then if you count all the Bohr radiuses, it's 1 over Bohr radius to the 4th. And then we get this integral, r to the 4th, e to the minus 3r over 2 Bohr radius. And when you work that all out, that's equal to 2 to the 15/2 over 3 to the 9/2. These integrals always seem to have 2's and 3's to powers, to nice powers like that, and times the Bohr radius. Okay, so that's all there was to the radial integral. And so now we need to do the angular integrals. So angular integrals. So fortunately, some of them are still going to be 0. Okay, but things we're going to need the YLMs that are relevant. So Y0, Y10 complex conjugate, it turns out you can look that up, and it's square root of 3 over 4 pi cosine theta. And then Y1, we might as well do plus or minus 1 together. That is equal to minus over plus square root 3 over 8 pi e to the plus or minus I phi sine theta. Okay, so we have to plug those things in, those angular dependences in, together with the angular dependence that's hidden within our vector that's appearing there. Okay, so there's nothing for it but to just go ahead and start calculating these things for different values of m. Okay, so let's do m equals 0 first. So we need to calculate I angular. Let's start with the z component of I angular. So if we put in all those constants, there's a square root of 3 over 4 pi. Our usual phi integral, nothing depends on phi, so that's just going to give us 2 pi. And then finally our cosine theta part, which is cosine squared theta. Okay, so this gives us 2 pi. That gives us a factor of 2/3. And so the whole thing is just 1 over the square root of 3. Okay, so if we've done one component of one of the three integrals, three integrals meaning m equals 1, 0, and -1. Okay, and we're doing m equals 0, so let's continue on. We can do I angular x component. But fortunately, that's going to be 0. And the same thing for the y component. And why are they 0? They're 0 because of the phi integral. So instead of immediately writing stuff down, you can just notice that, aha, these are going to have just cosine theta dependence. And if we go up here, these have cosine phi and sine phi dependence. And so when you integrate over a full cycle in phi from 0 to 2 pi, the integral of cosine phi is 0, and the integral of sine phi is 0. And the reason that didn't happen for the z component was there was no trigonometric function of phi there. Okay, so these are just 0. And so we're actually done with the m equals 0 case, which is good news. And so now let's do the m equals plus or minus 1 case, and we can do them at the same time. So this time, I angular z component is 0. Okay, and so why is that? Now our YLMs have e to the I phi's in them. That means they have trigonometric functions of phi, whereas the z hat, if we go back up to the z hat, that didn't have a trigonometric function of phi. And so once again, when we integrate phi from 0 to 2 pi, you integrate a single trigonometric function, not sine squared, but just sine or cosine, you get 0. Okay, so that's again because of the phi integral. Okay, so a good strategy is to scout ahead by looking at the phi integral before doing any of the rest of the integral to figure out whether or not it's destined to vanish. Okay, but now it's the x and y hat parts that are hard or relatively hard. So I angular x is, we're just going to put in the appropriate YLMs written above. Which gives us that factor. And then the phi dependent factor looks like this. E to the plus or minus I phi cosine phi. I guess I need a d phi there. And then there's minus 1 to 1 d cosine theta. Okay, and then the x part gives us a sine theta. And the YLM gives us the sine theta, so it's actually sine squared theta. Okay, so that integral is 4/3. This integral right here works out to be pi. And so this whole thing is minus over plus 1 over root 6. So we've managed to do both values of m plus or minus 1 at the same time. And now we've got the last thing we need to do, which is I angular y, which is minus over plus square root of 3 over 2, 1 over 4 pi. The difference is our phi integral has a sine phi in it rather than a cosine phi, but the rest of it's the same. Okay, so that's once again 4/3. This turns out to be, when you do that integral, and you can do it by taking the e plus or minus I phi and writing it as cosine phi plus or minus I sine phi. In any case, that works out to be plus or minus I pi. And so this works out to be minus I over square root of 6 for both plus or minus signs. Okay, so we've now worked out all the integrals that we need, and we just have to multiply them together in the appropriate spots to get the matrix element. So first, let's do the 2, 1, 0 state, matrix element 1, 0, 0. And we're going to square this thing. So when we square it, what's happening is, in this case, we're just squaring this one number because these two are both 0, right? And so this is just multiplying all the things together. There's a 1 over square root of 3 squared, 2 to the 15 halves Bohr radius over 3 to the 9 halves Bohr radius. That gets squared. And so the whole thing is 2 to the 15th power over 3 to the 10th power Bohr radius squared, which is 32,768 over 59,049 times the Bohr radius squared. Okay, so sanity check. This is a matrix element of the position operator, and then we're squaring it. So it should have units of distance squared. Bohr radius is a distance, so indeed it's a distance squared times a number, which just happens to be that rational number. Okay, so if we were going to do just the decay of the m equals 0 state, we would be done, basically, because we have the matrix element. But we're doing all of the 2p states, so that means we do the plus or minus 1 states also. Okay, and so we also want those matrix elements. And it's a little bit more complicated because now there's an x part and a y part, but not a z part. So the x part, I do minus over plus 1 over root 6 squared. And I have to add to that the minus I over root 2. Remember, we're taking the complex conjugate squared. So it looks like that. And then I'll write plus 0 there for the z part. And then the radial part is the same. Okay, and when you work this out, it's exactly the same answer. So I should maybe write same there. Okay, so the matrix element for all 3 states is exactly the same. Okay, and so for all n equals 2, L equals 1 states, we're getting the same transition rate to the ground state. And we can put all the numbers in now. Okay, so the rate to go from the 2p to the 1s state by emitting a photon is 4/3 fine structure constant omega cubed over c squared, which we worked out earlier. And now we're putting in our matrix element, 32,768 over 59,049, Bohr radius squared. Just have to put in all the numbers. 4/3 fine structure constant is 1 over 137. We worked out what omega was. So it's this. And then the speed of light is 3.00 times 10 to the 8 meters per second squared. And then there's our 32,768 over 59,049. And then there's our Bohr radius, which we can look up numerically as 5.29 times 10 to the minus 11 meters. And that gets squared too. And just multiplying those all together gives, it turns out, 6.25 times 10 to the 8 inverse seconds. Okay, and so our lifetime is 1 over that, which is 4.1 times 10 to the minus 7. Or sorry, I'm writing down the wrong thing there. That's 1.60 times 10 to the minus 9 second. So if you've got a hydrogen atom in the first excited state and you want to know how long does it last before it spits out a photon and turns into the ground state, the answer is about a billionth of a second. Okay, so things one should check when one's done a calculation like this, ideally, are first of all, you want to make sure that the rate isn't too large, because if the rate is too large, that might mean that the whole basis of your calculation was wrong. So in this case, the thing to compare is h bar times gamma. Gamma has units of time, and so h bar times gamma is an energy. And when you put in the numbers for h bar, this is 4.1 times 10 to the minus 7 electron volts. So the only thing we care about that at the moment is it's much, much less than the binding energy, which is just telling us that the width of this state viewed as an energy didn't disturb too much what the energy levels were. So there's not, if it had, then we would have had to think a little bit more carefully about what that might mean. But this is an extremely tiny energy shift due to the width. Another thing you can ask yourself is, we figured out the wavelength of the photon, or the frequency of the photon, so what's its wavelength? Okay, so wavelength lambda is 2 pi speed of light over omega, and you plug in the numbers, and that's 1.22 times 10 to the minus 7 meters. And so why is that important? Well, remember, we were using the electric dipole approximation, which means we were assuming that the wavelength was very large. And that's a small number, but it's actually large, because the thing we should be comparing it to is the Bohr radius. So this is indeed much larger than Bohr radius, because the Bohr radius is 5.29 times 10 to the minus 11 meters. So earlier, we had this general argument that in atomic transitions, the electric dipole approximation is probably pretty good when you're going between bound states. And this is just showing in this particular case that indeed it's true. So the dipole approximation is indeed valid. With several orders of magnitude to spare. Okay, so that was all about the 2p state. There are 3 2p states. It has degeneracy 3, and we showed that they all have the same rate to decay to the ground state. And one way of thinking about why that should be is the ground state is completely spherically symmetric. So it doesn't know or care about any special directions. And in particular, it doesn't know what the angular momentum, it doesn't know anything special about the angular momentum of the first excited state. So that's sort of why it will turn out to not depend on that quantum number as we checked. Again, the 2s state cannot decay to the 1s state in the dipole approximation. By emitting a single photon. That does not mean that 2s states are absolutely stable, though. Oh, so by the way, there was this selection rule that was completely general that said you can't have angular momentum 0 going to angular momentum 0. So this is never allowed for a single photon. So that's just saying that we don't have to bother worrying about, oh, maybe it's electric quadrupole or electric octupole. We already know it can't be magnetic dipole because that wouldn't satisfy the selection rule either. But this shows that it can't satisfy any selection rule by emitting a single photon. So how is it going to decay, or should there be lots and lots of stable 2s hydrogen around? And the answer is there isn't, because it can decay by emitting 2 photons. That's a much harder calculation. If you work it out, the lifetime for that is of order seconds, as opposed to billionths of a second. But the other thing that can happen to it is if the 2s state is sitting there, it's not usually in completely empty space. It might get jostled. And when it gets jostled by another photon, for example, it might turn into a 2p, and then that will decay. Or it might just get bumped into by another hydrogen atom or something like that. So you don't have to worry about there being lots of completely stable 2s hydrogen atoms around. They will decay, just much, much more slowly. Okay, and now for homework. Actually, let me talk about the homework in a little bit later. So let me mention about the midterm at this point. So some statistics first. The high score was an 85. The average was a 63.6. The median was a 60.5. And the standard deviation, otherwise known as the uncertainty, since we're doing quantum mechanics, was 16.6. And I think generally speaking, people did fairly well, except on problem one. Problem one, I thought was going to be a gift because I'd sort of warned you after the previous midterm that you might see again the dot product of angular momenta. And so you did, but apparently people forgot how to handle that. So I can warn you again that you just might see a dot product of angular momenta on the final exam, because I'm determined that we will all know how to handle dot products of angular momenta in this class. And just to show how determined I am, you're going to get to redo that problem and another related problem for homework coming up. So let me mention what's going to be on homework 9, which is not on the website yet, but will be either tonight or tomorrow for sure. So there will be redo problem 1 on the midterm. Let me give you some hints about that. First of all, some people wrote down some complicated integrals. There's no integrals at all to do on this problem. Some people tried to use Hund's rule. There's no Hund's rule either, because this is not a problem about atoms. Some people forgot, even though I think I said it in the problem twice, that these are not fermions. These are bosons. And so they do not obey the Pauli exclusion principle. And then last but not least, there's the fact that you're taking the dot product of two angular momenta. Okay. So in a minute, I'll say a little bit more about what to do in that situation, even though we've said it, we talked about it before. Okay, so that's going to be one problem. And then there will be a fixed version of problem 4 from set 8, where I'd made the horrible typo. And then there will be a problem of doing the decay of a 3D to 2p of hydrogen. And I'm actually choosing 3D to 2p to make it as easy as possible. If I'd chosen something else from the 3 state, it would have been, from the 3rd level of hydrogen, it would have actually been harder. And when I'm doing this, I'm going to only make you do a specific value of m. M equals +2. So what that means is, if you're comparing to what we did today, if we go back up to what we did today all 3 values of m, which cost us some extra time to do all these integrals and to think about all those integrals. Since I'm only having you do 1 value of m for homework, that will reduce the labor that you have to do for that problem. But otherwise, the strategy is very similar to what we did today. Okay, so that was, that will be out for sure tomorrow, if not tonight sometime, and due in a week on Thursday as usual. And then finally, we are nearing the end of the notes as they were originally given. So there will be a new version of the notes before you run out of things to read, probably on Sunday. I'll put that on the website. I think I'll actually email that to everyone. Okay, and so just let's go back to the dot product of angular momenta thing. Okay, for any two angular momenta, it does not matter if they are spins or one of them's a spin and one's an angular momentum, or they're both orbital angular momentum, or they're both orbital angular momentum of the orbital kind. Let's just call them J1 and J2. If you encounter their dot product, what should you do? So this is the trick. J1 plus J2 dotted into J1 plus J2 is equal to J1 squared plus J2 squared plus 2J1 dot J2. This is otherwise known as the total J squared. And now we solve. J1 dot J2 is 1/2 J squared minus J1 squared minus J2 squared. Okay, so we used this when we did the fine structure, the LS coupling. We did it in the hyperfine. We've done it in several problems now. So the key thing about writing it this way is that now it is super easy to evaluate this because you can choose a basis where these are just numbers. And that's the total angular momentum basis. And so this just becomes as numbers. So these are, right now, they're operators. But when I turn them into numbers, they turn into this. Okay, so that is the trick or the method that I'm determined you will all learn before leaving this class. And just to make sure you do, again, I'm warning you that you just might see this on the final exam. Okay, any questions about that? Or anything else about today's lecture? All right, so if not, then I will see you all on Friday. And on Friday, we will start with scattering, and we'll do it first for one-dimensional scattering. And we'll do a couple of examples, and then we'll quickly graduate to doing scattering in 3 dimensions. All right, so that's it for today. If there are no further questions, we can stop.
I had a quick question. As it stands right now, is the final going to be in person?
As it stands now, yes. Unlike last semester, it will actually be in person.
Thank you.
Sure. Any other questions? All right, then I will see you all on Friday.
Thank you so much. Have a good one.